Now let's take a look at example 3. Find the Maclaurin series for the function f(x) equals 1 plus x to the power m. Let's take a look. So for the Maclaurin series, it's the same as Taylor series, right? So firstly, we need to find all the coefficients, and the coefficients an f to the nth order derivative divided by n factorial, right? So f(x), let's see, to the m, and we calculate fa, that is our a naught, fa. So a here, in this case Maclaurin, that means f0. So we make x equals 0, so a naught is 1. Now let's take a look at the first derivative, f prime x m 1 plus x to the m minus 1, right? And let's take a look at second derivative, m minus 1 plus x to the m minus 2. Let's do one more. m minus 1 m minus 2 1 plus x m minus 3. And so our a1 is, let's write down f prime 0, which is m. F double prime 0 is m 1 minus m. M triple prime is m minus 1 m minus 2. Okay, so in this case, let's see, we can skip the middle steps, and then let's see what's the case order derivative going to be. M minus 1 m minus 2 and m minus, okay, so here is 3, here is 2, so this is 1 less than the order of the derivative. So here going to be m minus k, actually minus 1, so well, we open the parentheses, going to be plus 1 plus x and m minus k. If you look at here, they are the same, right? Okay, and in this case, case order 0 equals this plus 1. Okay, and in this case, we get the Taylor series or Maclaurin series for this function is 1 plus mx plus m minus 1 over 2 x squared. Okay, so write down the case term, minus 1 m minus k plus 1 over k factorial x to m minus k and plus. Okay, so this is the Maclaurin, and we call this binomial series. So definition 2. So the Taylor series generated by this function is called the binomial series. The Taylor series generated by is called binomial series. Okay, binomial series. M is just a constant, so in the future we can use a formula to find, for example, how to find the binomial series for this one, 1 plus x to the fifth or 1 plus x to the 1/2. Okay, we can just use the formula. Before that, let's take a look at another definition. Okay, definition 2, definition 3. Okay, let's take a look. The binomial series is given by this. Is what is given by this form. So we are going to write down the Taylor series in this way. It's going to be for x greater than -1 less than 1, 1 plus x to the power m. We write down this as 1 is the first term, and then we do this sum notation, okay, from 1 to infinity. Here m, k, x to the power k. So I'm going to give you what's the meaning of this one. So here we define m1 as 1, m2 as m minus 1 over 2 factorial. So you can see m3 equals what? m minus 1, so m minus 2 and over 3 factorial. So this is actually the coefficients in front of x to the power n, right, in the series. So let's see, the general mk, m minus 1, m minus k plus 1 over k factor. Okay, for k greater equal to 3. Now let's take a look at the example. So we start from the easy one. If m equals -1. Okay, and let's find the first several terms. So m equals -1. So if I write down m1, that means -1, 1, right? And in this case, this equals -1. So let's see, -1, 2 equals what? So here we have two terms, okay, on the top. So -1 times -1 minus 1, going to be -1 times -2 over 2 factorial is also 1. And let's see, -1, 3 equals -1, 3 terms. Now -1 minus 2 over 3 factorial. So going to be -1 times -2, -3 over 3 factorial should be -1. Something like this. Okay. So let's try to write down our function. This is the function, right? Generated by this function. We can get a binomial series, and m is -1. And then look at our formula. The first term is 1 plus, and then m1, which is -1 times x, okay, and plus 1 times x squared minus x cubed. Something like this. And if we write this a little bit, minus x cubed. Okay, let's try to do one exercise. 1 plus x to the 1/2 power. Okay, let's find the binomial series for this function. From this function, we notice that m is 1/2. m is 1/2. Let's see, m1. So we just need to find the first several terms. m1 is 1/2. Okay. m2, 1/2, 1/2 minus 1 over 2 factorial. So on the top should be -1/4 divided by 2, -1 over 8. Right. And m3. So it's 1/2, 1/2 minus 1, 1/2 minus 2 over 3 factorial. After simplify, so let's see, 1/2, -1/2. Here -3 half. Is that right? And divide by 6. Okay. So let's simplify. 3 cancel with that, which is 2 left. So this should be positive 1 over 16. Okay, so our binomial series we can write down this way. 1 plus x to the 1/2 equals 1 is always the first term, and then plus m1 times x and m2 x squared, and then m3 x cubed, and then plus, just like this one. Example 5. Let's take a look at the Taylor series for other functions. So now let's take a look. Actually, this is a binomial series. We can find the binomial series because we can write down this as 1 plus x to the 1/2 power, right? And actually, we just did that in the exercise problem. So let's write down the binomial series. Okay, and then let's take a look at the other one. If I say 1 minus x squared, root of 1 minus x squared. So in this case, we can look this as 1 plus negative x squared under the square root. Or we can just say 1 plus negative x squared and then to the 1/2 power. And then we find the binomial series. So in this case, we just change the binomial series, the x in the first binomial series, all the x into negative x squared. So let's see. 1 change this into x into negative x squared. So x squared. Right, so let me write down a little bit more detail. I can write down one more step here. So it's 1 plus 1/2 negative x squared, and then minus 1/8 negative x squared and the square. 1 over 16 negative x squared cubed, and simplify. Minus 1/2 x squared. So negative x squared become positive x to the fourth, and then minus 1 over 16 x to the 6th. Something like that. Okay, now let's take a look at the other one. Root of 1 minus 1 over x. 1 over x. Let's take a look. So this is same as the first one. Okay, we just change x into 1 over x from here. So going to be 1 plus 1 over 2x minus 1 over 8. Because x changes into 1 over x, so it goes to the denominator. 1 over 16 here, x cubed. Something like that. And if we try the exercise, 1 minus 2x to the 1/2 power, you can try. And here, let me give you the solution. It's going to be 1 plus, should be minus, right? Minus 1/2 times 2x. Okay. Change all them into negative 2x. Okay. Simplify. Minus 1/2 x squared, and here minus 1/2, because it's going to be 8 over 16 x cubed. Okay, so you can see if we know the binomial series, we can easily find other Taylor series for some other functions. Now let's take a look at the table of all the Taylor series commonly used functions. So here's the table, and you can use all the formulas in the future. Okay, so next I'm going to show you in the example 6 how to use this table to find Taylor series or do some evaluation. Let's take a look at example 6. So we want to express this function sin x squared as a power series. Okay. So firstly, let's find the Taylor series for sin x squared. So firstly, we can look at sin x. Sin x is x minus x cubed over 3 factorial. We write down sin x. And then what is sin x squared? Same as last example. Change all the x into x squared. X to the 6 over 3 factorial plus x to the square and the fifth tenth 5 factorial. Right? This is x squared. And then we do the integral of all the terms of the series. Dx. Okay, so for series we have the property we can do derivative and integral for each term. So let's see. This becomes x cubed over 3 minus x to 3 factorial times 7, right? Integral x to the 11 5 factorial times 11, because integral x n equals x to the n plus 1 over n plus 1. For example, x to 7 over 7. That's just the integral of each term, right? So this is the power series for integral of sin x squared dx. Then now you can try this one. Evaluate this as an infinite integral. So express this as find power series. Okay, here's the solution. E to the x is, look at the table, 1 plus x, okay, x squared over 2 factorial, x cubed is 3 factorial, then e to the negative x squared, 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, right? And then we do integral of each term, okay, which is integral of 1 minus x squared 3 factorial dx, and integral 1 is x, integral x squared is x cubed over 3, and here is x to the 5th over 5 times 2, which is 10, and then minus x to 7 over 7 times 6, 42, something like this. Okay. Now let's take a look at another application of the table. Okay, how to use the Taylor series. Example 7. So we want to evaluate a limit. So this is also the application of Taylor series. Okay, look at this. This is a 0 over 0 type. We can use L'Hopital's rule to find the limit, but here I want to show you how to use Taylor series to find this limit, because we may have some other very complicated functions. Sometimes maybe Taylor series is better. So let's take a look. Firstly, we change our e to the x into Taylor series, which is 1 plus x squared over 2 factorial, and then minus 1 minus x, okay, and x squared. x goes to 0. And you can see on the top we can simplify. We have 1, -1, x, and negative x. We have those. And also, okay, let's write down one more step here. X squared over 2, x cubed over 6. Okay, I changed the 3 factorial into 6. And now the numerator and the denominator both have x squared, so we can cancel the x squared, right? And here x left. So it's going to be what? 1/2 plus x over 6 and the plus. And in the other terms, they all have x squared, x cubed, or whatever. So when x approaches 0, actually all those terms will become 0. So the final answer is just 1/2. Okay, that's the limit. Let's see. So here is the exercise problem. Find the limit when x goes to 0, e to the x minus e to the negative x over x. So firstly, we write down e to x exponential function as the Taylor series for this function, and then we write down the Taylor for e to the negative x, and just combine them, simplify, and we find the final answer is 2. The limit is 2. So that's all we need to in this section, the Taylor series and the Maclaurin series. So we can have a quick summary what we did in this. So in this section, we learned the Taylor series and the Maclaurin series. And basically, we just want to express the function as a power series. And the power series, how to get that? We can write this out. Okay, f(a), f prime a, x minus a, double prime, x minus a squared. And the nth term is nth order derivative, n factorial. And the Maclaurin just means we make a equals 0, right? And then we find several Taylor series for some functions like e to the x, sin x, cosine x. We need to know for a given function how to find the Taylor series or Maclaurin series by ourselves, just by using this formula. And then we learned binomial series, that is 1 plus x to the power m, which is 1 plus m1x, m2x squared. Okay, and then we need to know how to find something like this by using the binomial series, like the formula, right? So you can try. And the last thing is a little bit application of Taylor series. For example, evaluate some limit, like the last problem. Okay, by using Taylor series. So in the next section, we are going to do more applications. Okay, we can stop here.